Hello everyone, welcome back. I'm Devavardhan Singh, and today in this video titled Linear Regression, How Machine Draw the Perfect Line. Let's be honest with the title. At the end of this video, you're going to learn and understand how a machine looks at a bunch of scattering data points and figure out a single best line for it. Okay, so now let's start with the section 1, why linear regression. Before we touch any mathematical, let's answer the obvious question. Why do we even care about linear regression when we have deep learning with us? Here are some of the things. Linear regression is your first tool to compute and to train any of the model. Before you throw a neural network to a problem, you try a line. If a line work, then you are done with that. Complexity isn't free. It costs you the interpretability, computability, and the explainability. Okay, so now let's talk about one by one each of the point. Speaking about the interpretability, that's the first big advantage. Every single coefficient in linear regression model has a direct plain English meaning. If I have a model predicting house prices and the coefficient for the number of rooms is 2 lakh, that means that adding one room is associated with the lakh or with the price of 2 lakh increase in price. That's it. No any black box and nothing more. Okay, second advantage is the efficiency. For a smaller data set, there's a closed form mathematical solution. So you don't need to train it iteratively. Your solution you can solve that in one equation only. Moving towards the third point, which is the foundation. Logistic regression, linear regression, it's only the linear regression with the sigmoid function. Then the rigid and the lasso, which we also called as L1 and L2 regression, these are for the regularization. So these all are having a computational foundation as linear regression. Now moving towards one of the critical assumption, and that is linear regression assume the relationship between your features and the output is linear. So that's a one important thing that you have to focus on. We'll be discussing it later also. Moving towards the second section, you have your features that are the input points like x1, x2, and all the way to xn. And you also have your target variable y, which is on a real number line. Now, your training set is just m examples, each being a feature pair. Now, the hypothesis function is how your model works. For example, for a simple linear regression, we have one feature input, and the hypothesis is y cap equals to theta naught plus theta 1 x. Now, here are some of the parameters which you need to understand. Two parameters. Theta naught is the intercept, it is the value of y cap when x equals to 0. Now think of it as a cross line. The y-axis theta 1 is the slope for every 1 unit you increase in x. Now the y cap changes by theta 1. If theta 1 is positive, the line goes up, and if negative, then it goes down. Now here we can modify it by using multiple linear regression, where y cap is equals to theta naught plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 and so on. Now the clean vector form of this is we can write as y cap equals to theta transpose into x. The matrix of theta will be taken and the transpose is done so that the matrix multiplication can be done. Okay. Now the most important part of this unit is the residual. Residual is the error of the change in y to y cap. Okay, it's the sign difference minus actually predicted. If the residue is positive, then we are under predicted. If it is negative, then we are over predicted. So our job is to make the residue as small as we can. Seeing here some of the geometrically, a picture of a scattered plot is being given. Your data points are being scattered around. The linear regression line is there, which you are fitting. The residue are those little vertical gaps, and the distance of each point is from the line is also given. So some of the points are above and some of the points are below. We have to minimize those gap collectively. Now moving forward towards the section 3, which is the cost function. So here's the key question, that why do we define to minimize those gap collectively? Okay, when we have a single number that summarize how bad the current line is, so that's what we called as cost function. Okay, we use this mean square error here, which is being written by J. Let's break it down. first of all, y cap minus y square. So now the most important question is that y square is here. There are two reasons. First one, squaring make every error positive, so positive and negative errors don't cancel out each other. Second one is how important it is to square, because squaring punishes the large error disproportionately. For example, you can understand this easier by plotting a graph for the absolute value and for the square values. Okay, now we have 1 by m. Why we divide by 1 by m? So dividing by the number of training examples, so that the cost doesn't just grow as we are adding more data to it. So it's averaging the error, not cumulating the one. Okay, now half. This half is purely a constant. This we get on differentiating the j to get the gradient. So the exponent 2 comes down as the coefficient, so to cancel it out we use half here. If you have worked with the other neural networks, then you have also in the neural networks, then you have seen that many other such constraints are being used there. Okay, now one more question that can be asked in your institutes and other exams, that is why we are not using the absolute values of error, MAE. Actually, we are not using it because at 0 point it is not differentiable. The MSE gradiently grows as you move further from the minimum, and it automatically takes big steps when you are far away. So that's a much better property for optimization. Now we have a graph where you can it's not a graph, it's a symbolic representation where you can understand it easily. The most important property of MSE, that it is convex in nature. If you plot j as a surface over theta naught and theta 1, you'll get a small bowl shape. This ball shape has exactly one bottom and one global minima, no local traps, no saddle points. Whatever optimization strategy you use is guaranteed to find the best answer here. Okay, so let's move forward towards the section 4. Now this is not so much important that you have to know the proof of OLS, but many a times some of the companies and they ask that if you know the proof for OLS is. So first of all, OLS is ordinary least square. Okay, the question can be made in different way also. That for example, you can be given points like x and y points, and then you will be asked that draw the best line which passes through them and minimize it. So these some question related to partial differentiation can also be asked. Okay, so now let's go step by step. First step is you need to find the theta naught. Okay, to find the theta naught, we'll take the partial derivation of j, which is our cost function, with respect to theta naught. Okay, yeah, once we have done with that, we'll set it equals to 0. Now expanding it, we'll get the equation as this, and now we're gonna divide this by m. Okay, you got a result as theta naught equals to y bar minus theta 1 x bar. Here y bar and x bar are the mean values of the given set which are given to you. Okay, now we are going to find the theta 1. To find the theta 1, you need to differentiate it with respect to the given solution of the cost function. Okay, now I have one more suggestion here. As this proof is given here, you can go through it, but if you want to find it directly, what you can do is you can get the values of the y bar, you can get the value of the x bar from the given data, you get the value of theta naught. So from there you can directly calculate the value of theta 1. Once you have the value of theta naught and theta 1, you can go for the further calculation. And otherwise also you can learn a formula which is theta 1 equals to convolution of x comma y by the variance of x. Okay, now moving forward towards the third step. In the third step, you directly get the multiple linear regression equation, the normal equation, which is gradient with respect to beta. So you have to directly learn this formula. This symbol we'll call as beta. Beta equals to x transpose x whole inverse into x transpose y. Now to tell you, I have a solution that how I have learned this. So basically what I did is you write it like x beta equals to y. Now take multiply x transpose both of the side, so it will be x transpose x into beta equals to x transpose y. Okay, now to calculate the matrix value and the vector value for beta, we'll take the complete inverse and take it on the other side. So finally we get beta equals to x transpose x whole inverse into x transpose y. So in one shot you get a one equation which can give you the exact solution for this. Here's a note for you that for the gate, it's very important that the matrix inversion step is O of n cube, big O of n cube. So you have to remember this, that for the small number of features it's instant. Okay, now let's move to another section. Moving to section 5, the gradient descent. Gradient descent is how we are going to solve the parameter iteratively when the normal equation is too expensive. Okay, so what we are going to do is we are going to use this update rule. Okay, theta j will be updated by theta j minus alpha into the differentiation of the cost function with respect to theta j. This alpha is a parameter which we also called as the learning rate. Okay, it's the step size for the differentiation of the for the differentiation of the cost function with respect to the theta. Okay, now why we are subtracting it? The gradient always pointed uphills on the cost surface, but we want to go to downhill, so we'll gonna subtract it. Okay, so now we again write the complete formula. We can notice here that the error signal get weighted by a feature value. Okay, it's get a weight as we have seen in the previous video also. So now the learning rate alpha is the most important hyperparameter here. Now discussing about the alpha, if alpha is too large, your step overshoot the minimum. The cost goes up instantly instead of down, or it oscillates. Okay, if alpha is too small, you are taking a very tiny baby steps, so you'll eventually get there, but it could take some millions and billions of iteration. Typically the values should start from 0.01 or 0.001. Now the hyperparameter is itself a term which tells us that you need to fine tune it accordingly. Okay, there are three flavors of gradient descent which we'll be gonna see in this. First one is the batch gradient descent, which uses all the m training examples for every each step. The gradient estimation is accurate, and the convergence is smooth, but it's also slow because m is large value, and when you are using it in using all the m values in every step, then it become a bit difficult. Okay, next, before discussing this HSGD, we're gonna first cover the mini batch gradient descent. So mini batch gradient descent is a sweet spot as it uses the k example per stages. Okay, k is typically between 32 to 256. You'll get a reasonable gradient estimation if it, and it's very gpu friendly. Obviously you are learning this course, so you obviously know what a gpu is and how computation and optimization work for it. Okay, now going towards this stochastic gradient descent, it is just one randomly choose example per step, super fast per update, but the gradient is too noisy. We can see it in the graph plotting also later on. Okay, so here's a quick example given to concern. For example, if m is equals to 4, learning rate equals to alpha equals to 0.1, and current theta 1 equals to 0.50. So how the updation take place? Okay, now moving forward towards the error matrices, which is the section 6. So now you are updated, you are trained a model. Now how do you actually measure that how good it is? Okay, so we have some of the matrices for it. For first of all, which we have already seen, is the MSE, mean square error. Okay, the most important issue, we have seen the pros for this. Now the cons for is that MSE is units. If you are predicting house prices in rupees, MSE will give the rupees squared, so that's not interpretable basically. Now moving forward, we have root mean square error. Okay, how it does it, that taking the square root, you will get back to the original unit. For example, if RMSE is 5000, then your model is off bought by roughly 5000 on a typical prediction. Okay, next we have MAE. We have already compared MAE with MSE, so you can just see the definition of it here. And let's move forward. There's one more fact which you can go through is that RMSE value is always greater than equals to MAE. That's proven by the Jensen's inequality. If you want to know more about it, then I can just go with that also, but just for now it's sufficient. Okay, section 7 contain a very important parameter, that is R square score. Okay, it's very important to get to know that what is this called as. It is called as the coefficient of determination. Okay, so here's a formula written for this. Let me explain you what it is. So the SS total, the bottom part, the denominator showcase the total sum of the squares, and the upper part showcase the residue sum of the square. Okay, the ratio of both of this tells us the fraction of variance your model failed to explain. Okay, just note my thing, that it showcases the fraction of variance your model failed to explain. Okay, subtracting 1 from it, you will get the fraction it did explain. Okay, so for the interpretability, you can go like that: R square equals to 1 showcase a perfect prediction, R square equals to 0.85 showcase that the model is 85% explainable and it's pretty good. For R square equals to 0, there is no better prediction for it, and the model is no better than just predicting the mean value of the y bar. Okay, and if R square is less than 0, then the model is worse than the naive baseline. Okay, visualization of this can also be seen here. We have one more parameter that is called as adjusted R square. This is mostly used for the multiple linear regression, and the formula for this is written here. Now let me explain you the parameter for this. So where here you can see n is the number of the features, m is the number of the samples, and if you add a useless feature, then the penalty from the denominator overweights any tiny gain in the R square, but adjusted R square actually drops. Okay, so this is the difference between the two. Let's move forward with the section 8, which compare the single versus the multivariable. So simple linear regression, as we have already seen there, we have secondly multiple linear regression also, and one more we have, that is polynomial. So let me first tell you the difference between the two. Let me write the equation for three of the variable linear regressions. So here what I have written is, first for the simple linear regression, second one I have written for the multiple linear regression, and third one is the for the polynomial linear regression. Okay, so we can't say anything like polynomial linear regression. It's basically polynomial regression. Here are the graph plots for theta 1 and theta 2. As you can see over these steps, we have already taken this all into account in the previous slides. Now there are two methods. One is the min-max normalization, that squeezes every features into the range of 0 to 1. That's good when the distribution is roughly uniform. Okay, secondly is the z-score standardization, centralizing the features at 0 and scaling it unit to 1. Okay, so basically the mean value we need to take it to 0 and scale the variance and scale it to the unit variance, means one variance, preferable when the data is approximated by the Gaussian or any normal distribution. Okay, moving forward towards the last section, that is first one is the linearity. Y must be a linear function of x, that we have already discussed and see and saw the graph curved also. Second one is the independency. Okay, observation must be independent and identically distributed. No autocorrelation should be there. A question can be asked where data set can be given to you and can be asked that is linear regression be there on it or not. So for that you have to find the autocorrelation for this. Thirdly, which we have also discussed previously also, but here we are going to discuss it in a bit detail, that is homoscedasticity. So the variance of the error must be constant across all the values of x. If you plot residual and then fan out like a funnel, as x increases wider on one side, that's heteroscedasticity. Okay, so your model is more uncertain for a large value than a smaller value. Okay, fourth one is the normality to the residue. The error should follow a normal distribution function with a mean 0. Okay, this we have also discussed there. There is a diagnosed QQ plot of residual that lies on the diagonal line. Okay, fifth point is the no multicollinearity. For example, in multiple linear regression, your features must not depend on each other. For example, x1 should be independent of x2. So that's a one important thing. And there is one more feature also called as VIF, variance inflation factor. Okay, we have not discussed it in more, but VIF above 5 or 10 is also a red flag. So, moving towards the end, the summary for this linear regression, we have derived some of the formulas for it. We have seen that how OLS works, how some of the errors like MSE, RMSE, MAE, when to use them, and how each of them are being used in the gradient descent. And we have seen the three variation of gradient descent. We have seen about r square and adjusted r square also, the five assumptions that are being taken into accountabilities. So here it is, we have completed with the linear regression. There are many other types of regression also, but moving to them, it's very important that this is the baseline which you need to understand before getting into any of the ML models and DL models and neural networks. So thank you.